Okay, so today we're going to talk about Newton's third law, and I'll start with the screen share of the workbook here. And again, that's on page 88. So I've alluded to this maybe a little bit before. However, this is probably the most commonly screwed up of the three Newton's laws. Students have a difficult time with this. Most students have probably heard this at some point in your life where you say, every action has an equal but opposite reaction. And so, yeah, let's, I like to think of it this way. If I push on a wall, the wall will push back on me the same amount in the opposite way. And you could do this. I did another example. A floor exerts friction on a mop. Well, the mop friction on the floor. The opposite is students. Here's the thing that students screw up all the time. They think, okay, there's a block sitting on this book. You could say, well, weight is pulling down on this block. And then you say, well, the book is pushing up on the block. The forces are balanced. They're equal in magnitude and opposite in directions. That must be what Newton's third law is talking about, right? Turns out that's totally false. That's not an action reaction pair, even though everything about it seems like it. Yes, they are equal in size. Yes, they are opposite in direction, but they're not the same. It's not Newton's third law action reaction pair. This is a better way to think about it. Okay. So here is this whiteboard. If I push this way on the whiteboard, right? So I'm pushing that direction on the whiteboard. Rob pushes whiteboard that way. The reaction to that is whiteboard pushing back on me the other way. That's very different than gravity, which is the earth pulling down on something and a different object holding it up, right? The earth pulls down on me using gravity. I pull up on the earth using gravity. Two objects in space are attracted to each other by gravity. So now the floor exerts a force upwards on me, which keeps me from falling down. I exert a force downwards on the floor, right? Think about it. I'm crushing the boards in the floor, or I'm putting some kind of force on there. Now, those forces wouldn't be happening if it weren't for gravity pulling me towards the center of the earth, but that doesn't make gravity and normal force an action reaction pair. In fact, action reaction pairs are always the same type of force on two different objects. So if I go back to this common misconception right here, when you have a block sitting here on a book, right, there are action reaction pairs. The earth pulls down on the block using gravity. Well, the block pulls up on the earth using gravity. Now, what's the difference here, right? We see that that same size force will have a dramatic effect on this little block, and it has almost no effect at all on the planet. Just like my gravity, when I exert a gravitational force on the earth, compared to the size of the earth, it doesn't do anything noticeable. That's why we don't think of it. Okay. It's not that it doesn't exist, though. Now, over here, you could say there's a normal force from the book upwards on this little piece of plastic. Well, similarly, there's a normal force from this little piece of plastic downwards on the book. And so we see that each force has an action reaction pair. This block has two forces acting on it, a gravitational force downwards and a normal force upwards. Each force, each type, the normal force and the gravitational, each one has an action reaction pair, and it comes on a different object, not this one. All right, so I'm going to pause for a second and see if there's any questions, because that's sometimes counterintuitive to people, or they don't like that. Of course, it's true. So you can't help it. It's just weird. Any questions about that? All right. And you can interrupt me at any time. You could ask Jay. Let's go back to the screen share and see if there's some thoughts that I have here. Okay, so look carefully at this list of crap and see what we see. Okay, it's equal in magnitude, opposite in direction. So notice if you include the vector symbol, it's an equal force but opposite direction. That equates to a minus sign in the vector. So notice if we're just looking at the magnitudes, we say the magnitudes are equal, but the force vectors are equal in magnitude and opposite. That's why if you include the vector symbol, you get the minus sign there. Okay, we talked about this, we talked about this. And this is something I alluded to. So this is a way to check your work. So if I ask you a question on a test, which I guarantee you I will, I do every year, usually on the next quiz or the final or both, and maybe even the next two quizzes. So you really should know this. I'm going to be looking for you to screw this up because most students do, and this is a big deal to me. I don't know, it's a pet peeve. Okay, so make sure you study this. If a force is a gravitational force, the reaction force associated with it must be gravitational. If a force is frictional, the reaction force must be frictional. So, yeah, the action-reaction pairs are always the same type of force. Either they're both normal forces or both frictional forces, etc. All right, so let's see what else we have in here. Avatar, blah, 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 blah. Okay, so here's an example, right? Let's say a zombie pulls up and to the right on the string using tension. Okay, well, what is the reaction to that? I just want to show you what I'm doing here. It's flipping the sentence. The zombie, instead of being the actor, becomes the person who's acted upon. We see that the string is the other object. That's still there. And we see the type of force. Oh, well, here's the direction. Up and to the right becomes down and to the left, opposite direction. And then finally, we see the type of force does not change. So what I have discovered is it makes it easier for me to make sure I get the action and reaction pairs correlated correctly. If I write out a sentence and say, object 1 exerts a force on object 2, here's the type of force, and here's the direction. So those 4 pieces, right? And I'm alluding to that, if I could scroll down just a little bit, right here. If I'm trying to get this done, and let's say on my test question, it says, the action force is blah, blah, blah. Give me the reaction. What I try and do is first write down a sentence for the action, then switch the object, switch the direction, but leave the type of force the same. If you get used to this, I think these become very, very straightforward. Here's an example. The Earth exerts a downwards gravitational force on a zombie. Well, the zombie exerts, flip the direction. Instead of downwards, the zombie would exert a force upwards. It's the same type of force. It's still gravitational. And then you switch the objects, right? The zombie and the Earth have switched place. A couple of things students screw up. Remember this. Objects exert forces on objects. They do not exert forces on other forces. So you can't say you exert a normal force on gravity. That doesn't make sense. You can't say you exert a frictional force on the speed or the accelerate. That just doesn't make sense. So when you're writing these sentences, you got to remember this forces you to say, okay, what is the object exerting the force and what is the object experiencing the force? Okay. So in your action-reaction pairs, you'll notice this pattern. The action of an action-reaction pair is always acting on object 1, while the reaction is always on the other object. Okay, they always act on different objects. They always point in different directions, same type of force. And this is true whether they're accelerating at constant speed or at rest. Let me pause for a second. That's a lot of words. I don't know. Any questions on that? Jay, anything you would chime in on this or no? Anything that you found that works for you or any thoughts?
Definitely making sure that you put the same reaction force because that killed me a couple times on the tests and on problems, is use the same force. It's
Yep.
not going to change.
Yep. Yeah, you just kind of, it's counterintuitive, isn't it, Jay? Like, why, do you know why it was hard to learn this? Because it's like, I don't know.
I know for a lot of it, I kept thinking that if I had, say, a box on the ground, then I would
Hmm.
have gravity from the box to the ground.
Hmm.
But then I would have a normal force from the ground to the box. And I thought that was the reaction pair, but it's
So
not.
would you say it's fair to say that when you're first starting, you tend to focus on the directions of the forces to think about equal and opposite instead of the
Exactly.
type of forces, right?
Yes.
Yeah, yeah. And I think if you can get to that point where you think, okay, instead of thinking about what's pointing the opposite way, first think about the type of force and the objects, and the rest will just work itself out, hopefully.
Exactly.
Yeah. And as strange as it is, I wouldn't hammer on this if I didn't think it was actually useful in doing actual problems. It's not just like some fact that's like, okay, cool, whatever. It turns out we use this in chapter 6, especially with frictional forces and normal forces all the time. I don't know. I would say that's true, right, Jay? Do you remember thinking about these in that chapter a lot?
Yes, definitely.
Yeah. So we're going to use this all the time. You might as well get it right. And that'll help you in Physics 161 too. Okay. Let's go back, see if there's any other nuggets in there. And you can see the common one she was talking about. And so Jay is pretty darn good at physics, right? And you could see she was making this classic mistake. And I said it in here 3 times. I've had to teach other physics instructors this one. They're like, wait, isn't it? I mean, I'm telling you, you just, yeah. I think I can prove this to you right now, once and for all, that normal forces and MGs are not action reaction pairs. Whoops. Let me show you this. Let's imagine we have a block and we're sitting in an elevator. And let's say this is supposed to be an elevator and it's accelerating up. Okay. And so here's a block. If I draw the FBD of the block, there's a normal force up, there's mg down, and maybe this thing is accelerating with some rate a. In this case, when I look at this, n minus mg equals ma. And I just want to point out that n is not equal to mg. Right? So if there's one case where they can't equal, they could never be action reaction pairs because they'd have to be action pairs all the time. It's impossible for normal force and mg to be action reaction pairs because there's at least some instances where they're not equal in magnitude. That solves it. But yeah, that evidently that's not obvious enough. So what about another case? So how about this? What if you got a block on a ramp? The normal force points this way, mg points this way, cannot be action reaction pairs. They're not pointing opposite directions. So in all, yeah, so it's just, yeah, I don't know how else to say it. We get lulled into this false sense of security when you have a block sitting here and it's at rest, and this situation, A equals 0, there'd be a normal force this way, there'd be an mg this way. In this particular case, they're equal, they're opposite, but they're not action reaction pairs. So, all right. Okay, so let's go do some practice problems right now and try this out. There's nothing we could do now but just practice. Oh, exactly. Another classic thing you could say is because they occur on different objects, you cannot see the action and the reaction on the same FBD. Think about it. Here's the let me do a variation on this. Here's Earth. And let's say there's a box sitting right here on the Earth, right? So I know that there's a normal force holding up the block. Well, on the Earth, that same normal force is downwards. Oh yeah, Yeah, it's a big box. Hopefully it's a big box of Doritos that I could be eating later today. 600 billion trillion tons of Doritos ready to go. Okay. Let me add some words here. This is the normal force of Earth up on box. And just so I have the vector, I'm going to put this here. Whereas this one will be the normal force of the box down on Earth. This is not a free body diagram because we have more than one body, right? Let's see here. So now in this case, there's also another force, mg. In this case, this would be Earth pulls block down using gravity. The type of force is a gravitational force. Well, similarly, here's the center of mass of the Earth. There's the box pulls Earth up using gravity. Now, if I draw a free body diagram of the box itself, all I'm going to see is a blue arrow and a pink arrow. And notice these are not action-reaction pairs. The blue arrow is an action-reaction pair with this blue arrow. This pink one is an action-reaction with this one. So you're right. This would be the FBD. And notice these two are not an action-reaction pair. They're acting on the same object. Reactions act on different objects. So excellent way to think of that. That's a good thing to remember, right? So if you're on test day and you're reaching for that reaction pair, well, you know the right answer cannot be any of the other forces on the same object. So at least reach for something crazy. Maybe you'll get it right. Yeah. Okay, that's a very sneaky but helpful trick. All right, let's see what else we've got in here. All right, so, oh, no fish face slapping. Oh, okay, I would slap you with a face and the fish. All right, so here's a couple of examples. So let's take a minute and I'm not actually a huge fan of breakout rooms, but this one is so important that you talk. I may actually, let me see how many people we have. So this is page, let me make sure, page 89. All right, what I'm going to do is just split the class in half with 2 breakout rooms, all right? So let me just do this. And I'm just, so this should be, hopefully there's going to be a couple people in there, and I want you to try and actually talk through these. I wouldn't be wasting my time with breakout rooms if I didn't think it was important for you to talk. So I'm going to create these, and then Jay, you and I can just pop in and out, okay? You go to whatever you want, all right? So let's do that. Page, what page? I think 89, Dom, page 89. Let me confirm that. Okay, and so go ahead and jump in those breakout rooms. I know I don't normally do this to you, so I'm not going to do it very often. Shoot, where was it? Yeah, we're on page 89, page 89. Okay, so Jay, how about you go into breakout room 1? Is that cool?
Yeah, that's cool. Which problem is it? Because I have the old one.
Oh, so do you have questions? So do you have 5.14 through 5.20? There's like a sun and then the guy jumping down.
Yeah, I have those ones.
Okay, and so maybe what you could do is let's give them just a minute to kind of start without us in there, and then just go in, and if they're having trouble talking, let me just let me assign her to a group. Okay. So Erica, we're doing some breakout work right now, and I don't normally do that, but I would appreciate if you could join that. And we're trying to do the problems on page 89. We're looking at Newton's third law and just trying to get people talking, okay, for this particular exercise. All right. So Jay, I don't know if it'll make sense to them, but yeah, let's just see how it goes. Just try and get them rolling. The really good questions to see if they know what they're doing are the two on the top of the next page. So if you feel like it's kind of getting stagnant and they know everything.
Oh, the blocks sitting next to each other.
Yeah, 20 and a half and 20 and 3/4.
Yeah.
So, all right.
Sounds
All right.
good.
All right. I'll let you go in there. I'll go to the other one. Or less if you're accelerating. Okay. Forces between two objects are the same whether they're accelerating to the right, left, up, down, or not at all. Now, forces on a single object, this one down here, let's read this. So, for example, let's say it moves to the right and speeds up. So that would mean A is going this way, right? Well, doesn't that mean the force 1 on 3, this force would have to be bigger? The circled force would have to be bigger if it's accelerating to the right. So it's a very different kind of situation. And notice if the acceleration was 0, those forces would have to be equal. They would also be opposite, but they would not be an action-reaction pair because they're on the same block. So I want to pause and see, while this is up on the screen, does anybody have questions about that? See the subtle difference between these types of problems. All right. Yeah. Oops, I thought I hit the stop share button. So hopefully that helps you distinguish this when you're talking about, when you're comparing two forces, two blocks in contact, or like the Earth and the moon where there's gravity or something. Two blocks exerting forces on each other, think Newton's third law. If there's a block in between two others, think Newton's third law. And I think that covers a huge number of cases that I've seen out of all the conceptual questions that I've seen as a physics teacher, which is probably a lot more than you. That seems to really get at the heart of this distinction. And that won't fix all your problems, but if you could really tell the difference between those two questions at the top of the next page, the rest becomes easier. That said, let's revisit 520, which one group wanted to look at, and I know the other group did and said it kind of messed with their brain. So let's just do a revisiting of this. Based off this, what do we see here? Person is in flight, makes contact with the ground. Okay, and so we see the normal force is varying, blah, 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 blah. Okay, so there's two forces on the person. Oh, okay. So when we look at this one, between stages 2 and 3, well, it's asking which force is larger on the person. When it says that, does this make you think of Newton's second law or Newton's third law?
I think of Newton's second law.
Why do you think that?
Because it's asking like which magnitude of force is larger on a person. So it's like either
You're right. You're right that it's Newton's second law.
Is it because it's talking about two different forces?
On a single object, which you know can't be action reaction. That's what I would say. Okay. Right? If we're talking about forces on a person, that's two different forces acting on a single object. That can't be action reaction crap. Does that make sense?
Yeah, that makes sense.
So your intuition was right. And I think maybe that was in there somewhere. And maybe, okay. So when I look at this one, I'm like, okay, they're on a single object. That makes me think sum of forces equals ma, because that's the only law we know to handle that. So if sum of forces equals ma, I better know something about the acceleration. Between stages 2 and 3, which way is the person accelerating? Tricky, isn't it? Well, let's think. Which way is the person moving?
Upward.
Is the person between stage 2 and 3, is their body going upwards?
No, it's downwards.
It's downwards. So they're moving this way. Moving is which letter? A, V, or X? When you talk about moving, we're talking about a person's acceleration or their velocity.
Velocity.
Velocity is downwards. As this person moves downwards, are they speeding up or slowing down?
Slowing down.
Slowing. So you're moving down and slowing. What does that tell you about acceleration?
It's upwards.
Opposite the direction, right? So which force has to be bigger? If the person's center of mass is accelerating upwards, who's winning the game? Weight or normal force?
Normal force.
Normal force. Isn't that trippy? So when you're hitting, think about it like this. Okay. Maybe you've tried this. Have you ever tried to like break a stick by jumping on it? It's easier to break a stick when you jump on it than if you just stand on it, right? Or sometimes if you step on something versus just very gently step on it. If you jump on a stick, it will break because it has to support more than your weight to stop you. So it's actually easier to break something by jumping on it than by just standing on it. So you probably have that intuition already. And so this is confirming that result. When you jump and when you land on something, the normal force has to push up harder than your weight is pulling down. Otherwise, you won't stop and you'll just go through the center of the earth and burn up. Ooh, that'd be something fun to do, but we'd probably need a lot more acid to get that to work successfully. And we don't have the funding for that. It's ERT mode. All right. Jeez. It's been a weird day, man. Okay, let's go back. So there's that. And now let's take a look at this. On stage B, stages 2 and 3, Earth exerts normal force on person. Person exerts normal. Okay, what type of problem is this right away? Newton's second law or Newton's third law?
It's Newton's third law.
Yeah, what gave it away to you?
It talks about how there's different forces exerting on each other, or the same force exerting on two objects.
Yeah, the two objects, right? Earth on P versus P on Earth, you see the subjects get switched. That's a clear indicator this is a Newton's third law analysis, right? Now, I know I'm basically straight giving you tricks to read my questions, but the whole point is these tricks to identify in these questions should hopefully identify you situations in real life when you would use second law versus third law. All right, and then this one, obviously, that's Newton's third law because it says action reaction. So I hope that kind of helps a little bit on this. If you're looking at two forces on a single object, think about force, acceleration, and things like that. And then otherwise, it's Newton's third law. It's almost like, oh, thank God, it's Newton's third law. Everything's the same. Done. All right. Let's see where we're at here. All right. Oh, this shows you a great way. Sometimes on paper tests, I'll literally do this and fill in the blanks, and you'd be surprised. People will miss this all the time. But if you get used to writing the sentences like this, you can write all of your action-reaction pairs in this format. Okay. We kind of talked about those ones. Maybe I'll end with this classic story and call it good today. So it turns out, I think it was the New York Times or some newspaper way back in the day. We're talking like the 1900s or something. And this newspaper says, it said, rockets in space are the stupidest thing I've ever heard of. It could never work. There's nothing to push against. Well, it turns out you don't need an atmosphere to have rocket propulsion. We obviously know this now. We've seen things in space all the time or heard about them. But the main thing that this newspaper couldn't get right, and they were like making fun of it. They had to publish a correction, and it took them like 100 years. They're like, whoops, we forgot to say that rocket propulsion is possible. But you could think of it really simply like this. Imagine this was not a calculator, but instead a bowling ball. You know what would happen if you throw a bowling ball that way. It's going to push you backwards a little bit. And so what is a rocket doing in outer space? Imagine the fuel inside the rocket being like a bunch of bowling balls, and then it's just basically a machine that's throwing bowling balls out the back. And every time you throw a bowling ball out the back, well, it's really a puff of fuel and smoke, and it flies out really fast. And that is actually the force that's making a rocket ship go forwards, right? If you throw fuel out the back in the form of exhaust, the spaceship goes forwards by Newton's third law. You don't need an atmosphere to do that. So if I find that link to that old story, I'll send it to you in a Canvas announcement. Yeah, let's see. I think we should probably call that class today. I don't normally end class early, but no, let's look at one other thing. Let's look at one other thing here. Yeah, sure. If you have an unlimited supply of free bowling balls and a bowling ball launcher, you could do it. Let's talk about systems really quick, and we'll pick up on systems next time more, but let me just foreshadow this. So I'm looking at the top of page 91, all right? Page 91, we want to talk about systems. So I'm just going to start with this one right here. And it looks pretty similar to the top of page 91, but you could just watch me in here and then read it later, okay? So let's say you have two blocks. And let's say a run-of-the-mill grade 1 zombie comes along and applies a force here. We'll just say this force has magnitude F, and it's that way. Okay, and so you probably have no trouble thinking, all right, these things might accelerate this way. All right. And so it turns out you could actually view blocks 1 and 2 as a single object and call it the 1-2 system. Okay. So a lot of times when we have two objects that are going to move around together, we can save some time and learn some tricks by grouping the two objects together. Now, there are some things that you can't learn about when you group these together. In particular, this might make sense to you at this moment. Think about it. If I push on these two blocks, what are some of the forces that are acting on them? Well, let's just do an FBD for object 1. Okay, so for object 1, what's one force that acts on it? Anything.
Normal force.
Normal force. Okay, and so I'm going to call this N subscript 1. So we're going to start to need to use subscripts next time when we talk about this, because there's a normal force due to object. This would be the floor on object 1. Okay, somebody else, another one. On object 1.
The applied force.
Okay, so we'll call that F to this way. Got it? The zombie force. Got it? What's another one? I could wait all day for it.
MG.
Always the MG. Okay. Now, I better be careful. It's quite possible and even plausible that these two don't have exactly the same mass. So I'm going to put an M1 right there. That's supposed to be M1G. Maybe I'll write it a little neater, more neatly, excuse me. M1G. Okay, is that it? Any other forces or no? On just
Friction.
block 1. What's that?
Friction?
Okay, there might be some friction. Let's say friction is negligible right now. So yeah, okay. Anything else?
There's a normal force between block 1 and 2.
So which way does 2 push on block 1?
Left.
Oh, so I'm going to call that normal force of 2 on 1. Now, what about on this? Let's look at the FBD of block 2. Okay, well, I know there's going to be a normal force up, and I know there's going to be an M2G down. I'll do those two. You guys got that right away. Other forces. Are there any other forces acting on block 2?
There's also a second normal force.
Ah,
That-
which way?
To the right.
Okay, and what's causing that normal force?
1 on 2. Or the box, the first box on the
You got it. I got you. I know what you meant. Yep. And so here's the idea. What we have been talking about all day is this one force. So we see in this case, it's pretty straightforward. We say, oh yeah, we could tell that this normal force is pushing to the left on 1, but it's also pushing to the right on 2. So, and these are not great yet until I put in the fact that these are accelerating. That tells us all the information we need. Now, here's what's cool. Because these are being pushed and they're moving in unison, they actually have the same acceleration magnitude and direction in this case. So we know that both of these are accelerating to the right. Now, if you take these equations and add them up, I just want to point out that you could actually think of these as being one object right here. The 1-2 system would look like this. If I did a system FBD, look what happens. Well, I'd have a normal force from the floor. That would be like these two. I'd have the two weights. So I would say M total G. That's the total weight. Then there'd be a total normal force up. And then there'd be a blue force this way, which was the applied force from the zombie. But what happens to this one and that one? They're equal in magnitude, opposite in direction, regardless of the acceleration. The two green arrows drop out because they would, you could draw them, but they would cancel out. So notice if you draw a system FBD, it's actually easier to learn about the acceleration. A system FBD makes it easy to do math, and we learn that, oh, well, the acceleration relates to the force, and the total mass. Got it. If you need to learn about the internal forces, the forces inside the system that get dropped out, drawing separate FBDs helps. Now you might be saying, well, why would I ever need to know this? What if you're working for some shipping company and you want to know how much force a box can withstand before it gets crushed, because you don't want to have to keep shipping out new products every time they get crushed? So there's a reason you might want to understand the internal forces sometimes. But this is going to be where we pick up next time. It's almost time for class to end here. But the idea is there are things called system FBDs where we group objects together in certain special cases. The only time you can group them is when they move in unison like a single object. If object 1 was accelerating faster than object 2, it would be crushing into object 2. That's a different problem. We wouldn't treat them as a system. Or if object 2 was accelerating faster than 1, well, they're separating. We wouldn't want to treat them as a system. But if they happen to be sliding along, moving in unison as a single object, that's when we can do this trick. And it's easy to solve this FBD first, and then use that information to solve either one of these two and learn about the internal forces. So, and then I guess the last term of this would be external forces. External forces are forces which are not internal. So here, basically everything except for the internal force would be called an external force. And we'll pick up there next time. We're going to do some worked problems there. And you'll see that that is when we will apply the Newton's third law all the time, because we need to understand this one piece to get one part of the FBD and understand all this crap. So that's where the Newton's third law fits in terms of computation.